Greetings and salutations, my Python-loving friends. Welcome to a pre-recorded session of my talk, What is new in recent versions of Python, that I gave at Jen at the Python Guild. So this talk is gonna be a live demo accompanied by various examples. There is a link to all the examples, so if you go there, I will post a link below the video. Then clicking on the examples, and also here you can see the links to all the material that I used while preparing the talk. So you can then check it out. My primary focus is gonna be on features, on language features, or some interesting things that are related to that. I will kinda disregard the performance improvements in each Python version, and also other like smaller features like improved error messages. But in general, I would like to advise to use as latest Python version as possible, because really the performance improvements that are there and the error messages are more clear, more understandable, and so on. And also, last but certainly not least, my selection is like highly opinionated. I put there what I believe was interesting, what I wanted to showcase. So if you have any other favorite features, feel free to share with your fellow viewers in the comments below the video. All right. I'm gonna cover 4 Python versions, 3.10 through 3.13, which at the time of recording is to be released in October 2024. The reason why I decided to include Python 3.10 as well, even though it's fairly old, like from 2021, is that there are some features that might be useful to you, and you might be unaware of those features, and some of them I haven't seen used in the code that much, so I would like to describe that as well. So let's begin with Python 3.10, and the first item on our agenda is so-called structural pattern matching. If you are familiar with languages like C, C++, Java, they have that kind of switch statement, which you can use to switch based on the values that a variable might hold. So like in this case integers. And Python didn't have that until Python 3.10. But in Python 3.10, this feature is much more robust. It's like the switch statement on steroids, and resembles more matching in, let's say, Scala or Rust than in C, C++, or Java. So let me give you a brief introduction. First of all, let's create an enum, like colors, enum, and we're gonna define 3 colors, so red, blue, and green. Then we're gonna create a color, so let's choose red. And we can then match on the different colors in this way. So this could be colors red, and here we can print something like red. And if we run it, obviously the code got executed. So this clause got matched, and the statements that are there got executed. We can do another color like green in this way, green, and obviously we need to change this if we want the code to get executed. If we want to handle all the remaining cases, we can use the wildcard in this way. So in this way we can handle like future colors that might be added in the future. Or we can like raise an assertion error like unknown color, whatever you want. So yeah, let's go in this way, and if we set it to blue, we see that the wildcard got matched. So that's not terribly interesting, but it illustrates like the very basis of the match statement. So let's do something different. we're gonna need data classes, and we're gonna define the point, a two-dimensional point with x and y. And then we're gonna create a point like 1 or 2, and we can then match the point, and we can match the structure of the point. So for example, this is trivial. So in this case, we might want to print something like origin. So let's change this and execute the code. Sorry. And we matched that point. So in this case, the instances are matched by identity. The only exception is the Boolean values true, false, and none. These are matched on identity instead of equality. We can also match while binding a variable. So in this case, let's change this. And then we can print x. So in this case, any point having the y coordinate set to 0 will match, and the value of x will be bound to the variable named x. So if we run the code, we see that x is 1, which is true. We can also match multiple patterns at once. So in this case, we can even match situation like 0 and 1. Yeah, or let me change this in 2. Yeah. And the next thing what we can do, we can match with a so-called guard, meaning that we want to match only certain points. So for example, if x is less than y, we might want to print, I don't know, just this. So let's do it this way, and we see that this got executed. And although I'm not going to show you any more complex example, you can basically pattern match on whatever you want, like even something like this, I don't know, that, and so on. Like that's perfectly valid, and it will work as long as you know you have those classes which take those parameters. So it's fairly useful because you can then match based on the structure and in a declarative way, instead of doing, you know, when if else if stream. So this might be more readable and simple. And the last example that I would like to show you is how to match built-in data types. So let's create a dictionary, name, say Petr, age, I don't know, let's say 30, city, I don't know, let's say Brno. And then we can match the dictionary. And for example, we might want to match all the cases where the name is Petr, and we want to get that age in a variable named age. And we can print, for example, Petr is years old, right? And if we run it, we see a match. Yep. So that's basically it. So you can pretty much match on anything that you want. All right, the next feature, it's called a new type union operator. So let's clear this. Basically, before Python 3.10, if you wanted to create a function that has for example, an argument or a parameter that can be either, let's say, a string or an integer, you would need to import the typing module and then use typing union, and here you would put string or int, right? In this way. But In Python 3.10, what you can write is just str or int. By the way, this is the classical bit or operator from Python. There is nothing magical. I will explain this in a greater detail later. And also, instead of writing typing optional str in cases where you can either pass a string or none, you can write just str or none, which is easier to type and arguably more readable. You can also use this syntax in isInstance or isSubclass checks. So if you want to use isInstance like 1, it's either string or integer. This will of course return true, and you can use it in this way, and similarly with isSubclass. And yeah, so now you might be interested, like what's that object? Like we can print int or str, and if we print it, like that's its representation. But if we check the type, we see that it's a union type, which is automatically created by Python. By the way, this type is similar to typing union, and the Python developers are planning or would like to consolidate these two types so that there aren't two types but just one. And by the way, this code works by calling the dunder or method on the meta class. So in this case, it's going to be the type meta class, and the or method on the meta class creates that union type for you. So this is how it works. Well, let's move to Python 3.11, where the first feature that I would like to describe deals with groups of exceptions and a special form of an except statement. So as you might remember from in Python, you can only raise a single exception and deal with a single exception at a time. But there are cases when you might want to deal with multiple exceptions. For example, when dealing with concurrent or asynchronous code, several tasks may fail and you want to gather all the exceptions and raise them to the caller. Or also when retrying certain functions like socket.connect, there might be multiple failures during retrying and you would like to return all of those failures. Or if you have multiple callbacks, they can fail. So once again, you would like to return all the errors. Or maybe even during cleanup, when an exception got raised and you are doing finalization, there might be an exception, so you might theoretically want to raise the original exception, including the new exception which was caused by the cleanup. And in Python 3.11, we have support for exactly that. So let me give you an example. So let's clean this up. We're gonna define a function, and we would like to raise multiple exceptions. So let's create a list of those. So for example, it can be an OS error, or we can raise, I don't know, system error. It doesn't really matter in this way. And now to raise those exceptions, we have to raise a so-called exception group, where the first parameter is the exception message. So here are the errors. And the second parameter is the list of exceptions. So let's call it and see how it looks. So now what we can see is that the default exception handler got executed and it printed out the name of the exception message, and told us that there are two sub-exceptions, where this is the first exception and this is the second exception. All right, so let's try to catch that and do something with that. So once again, like we can catch this as a regular exception, right? And we can print the type of the exception, and the exception itself. And we can see that what was caught is that exception group, and that's the same message that we saw earlier. And if we want, we can catch that exception group in this way, and then the exception object has this exceptions field, which contains a list of all the exceptions in the exception group. So now you might be thinking, well, like this was possible in Python before, so why I'm making so much fuss about it? This is when the extended except statement comes in. It's suffixed by an asterisk or a star. And if you do this, Python allows you to match just some types of exceptions from that exception group. So for example, if we want to handle all the OS error exceptions in the exception group, we can do it this way. So let's just do it and print it. And if we run the code, we can see that our print statement got executed. But what is interesting is that the default exception handler got also executed, and we see that it basically handled the remaining exception, which is the system error. So in this case, when using this form of the except handler, if you don't handle all the exception in the exception group, those exceptions are going to be re-raised in an exception group. So what we can do, we can also handle the system error. Let's handle it in the same way. And now we can see that both of these exception handling blocks got executed. So you might see a difference between regular exception handling and this exception handling, where in the regular exception handling, if there was an exception raised or handled, the other exception handlers wouldn't be executed. But in case of the exception group, multiple handlers can get executed. So this can be useful in situations like I described, but bear in mind that this form of except statement is not supposed to become the new default. You should, as per the documentation, use it only in cases where the function describes in its API that it can raise multiple exceptions at once, and use this only in such cases. So this is not supposed to be like the new meta of Python programming. It's just a special case. The next feature is also related to exceptions, and they can be now enriched with so-called nodes. So let's clean it up, and let's create a new foo function, and then we're gonna just raise a new error, my error. And now let's say that you handle that exception like in this way. So for example, value error as exception. Now you do some work here, and then for example, you might decide that, well, this is not I don't want to swallow the exception, I want to re-raise it. So you can raise it in this way. But you would like to notify the caller or the piece of code that it's gonna handle the exception down the track, to notify that code that you did something with the exception. And this is what the exception nodes are for. So here you can call the new add node function, and for example, I did this and that. And now if we execute the code, we can see the exception, the name of the exception, the error, and also below, this is what the default handler does. But in your code, you could go over the exception or the nodes and do whatever you want. So this can be useful in cases, for example, during test failures. The exception could contain additional details about the failure, or maybe you can put some advice into the nodes when the user does something which like your code doesn't like, to help them understand what is wrong. So there can be several uses for this feature. And of course, you might decide to raise a different exception, like my error, and maybe include that exception there. But in this case, you are raising a different exception. So if you want to raise the same exception that you accepted or got, then you should use those nodes. Another feature of Python 3.11 is that we finally have a built-in module in the standard library for parsing files in the TOML format. Just to refresh your memory, this is the file format that is used by many tools in the Python ecosystem. And you can use this file to configure the tools. So for example, pyproject.toml. This is what Poetry uses, and you can also use it to configure other tools like linters, formatters, and so on. And until Python 3.11, if you wanted to work with TOML files, you needed to use a dependency on a library for parsing TOML files. But now we have that built in. So let's clean it up. We're gonna import the library, and I have prepared an example TOML file here, which we're gonna read and parse. So we're gonna open the file .toml, read it in the binary way because this is what the toml-lib expects, and we can parse it, right? Load from F, and let's print it. And here you can see that what we get is a plain old dictionary containing the TOML file here. And that's basically it, at least now. You just get a dictionary, and you can then go over it yourself. There is no support for writing TOML files, just parsing and reading those. All right, so onwards to Python 3.12, where the first feature that I would like to discuss or show you is new syntax for generic functions, generic classes, and for declaring new types. So let's clear this up. And before Python 3.12, if you wanted to create a generic function or a class, what you would do is, of course, import the typing module, and then you would need to create your type variable by utilizing type variable and give it a name, and then you could create a generic function, for example, that takes an object of type t or inheriting from t, and then return it. But this has some drawbacks. First of all, this is a global variable. So if you are down the code, like 200 lines below, you might not immediately see that like this t is supposed to be only used like that function. So it's not locally scoped to that function definition. It is global. And to prevent like accidental use of that, people tend to prefix those with underscores, right? But this makes the readability to suffer. Hopefully, or I'm glad to tell you that since Python 3.12 we have a new way of doing that, so we can get rid of that. And instead, we can use the square brackets to define the type parameters of a generic function in this way. So this tells you that this function is generic over a type named t, which is the type of the parameter and also the return value. If you want to specify that t is supposed to be a specific type or its subtype, so for example, in this way, it tells you that it accepts parameters of type string or some subclass. You might also use this to define that it can be either a string or an integer or something that inherits from either of those. And similarly with classes, so you can have a class and defined in this way, so t, the generic parameter. So you don't have to work with like that generic t, which you might remember from before Python 3.12. So it makes the code cleaner, and the scoping is now improved. And also, in case you want to introduce your own new type, there is now a dedicated statement in Python, which begins with typing type. Then you type the name of your type. So in this case, we can define like this should be a string or an integer, and we can use this as a type. And now Python, like you see that it's treated as a type. So this is better than just writing like this. Also, if you want to create a generic type, so for example, list or set, you can do it this way, like list or set. All right. If you remember any other languages that have generics or templates like C++, Java, Rust, and so on, you might remember that those languages use those angle brackets instead of the square brackets. But the Python developers decided that the square brackets are a better fit for Python, because there was already a precedent in this case. This was already present in Python. And also the use of angle brackets has some technical limitations with respect to the lexer, like tokenizing the Python source code. So yeah, what we have is those square brackets. And by the way, let me show you an example from the PEP that introduces that. Here it is in all its glory. So if you are new to this kind of stuff, you might want to look at this piece of code and be not even sure whether this is Python or not. So like this is new, and just to read it. So this is a decorated function that has these type parameters, and the first function parameters is of type t. It has a default value. Then the second parameter is either an integer or string or some subclass, and then it accepts a variable number of positional arguments and a variable number of keyword arguments also typed, and returns the type t. So basically that's it. But if you see it for the first time, you might not even know that this is actually Python. The other thing from Python 3.12, it's also related to types. There is now an override decorator. So let me show you the decorator. So let's say that you have a class base and you have a method foo there, like this. And then you create a derived class which inherits from base. And we would like to override foo in this way, right? So far, so good. But maybe in the future, you decide to move this class elsewhere, and then you change the base class. So for example, by renaming foo to foo2 or to bar. But here we can see that it's no longer overriding the original method, it's creating a new method. So what you can use, you can import the typing module and use the override decorator, and then you will get a diagnostic that it seems that you are overriding something, but what you are overriding is not in the base class. So you need to fix that. And also yeah, this can be useful when changing basically the base class function, because Python or the type checker can now or linter can check that everything is how it's supposed to be. And by the way, when speaking about those decorators, this is from Python 3.8, I think, but yeah, not many people know about this, or arguably. But there's also a typing final decorator, which allows you to raise a diagnostic when someone tries to inherit from your base class. So this is similar to using final in other languages like C++. And the last thing from Python 3.12 deals with f-strings. And prior to Python 3.12, f-strings were kind of hacked into the language. They were like scanned or lexed as like regular strings, and there was no formal grammar, which resulted in several limitations of those f-strings. And also different interpreters could implement those f-strings differently. So like the CPython interpreter and PyPy could have a different implementation. So the developers decided that it's time to formalize f-strings. So f-strings are now properly covered by the Python grammar. And there are several improvements related to that. So let me show you those improvements. So let's create a list, I don't know, of people. So John, Alice. And let's say that you would like to print the list of friends, comma separated. So so you do something like friends, and then you would do comma, join friends, close it, and close it. So you would basically use a different type of quotation marks because you are already using those double quotes. But let's say that your coding standard says that you should prefer double quotes. So since Python 3.12, we can do this. We can use the same quotes, and it will work as expected. Also, it's kind of a maybe funny feature. I'm not sure how you would use it in practice, but Python 3.12 allows you, at least theoretically, to have unlimitedly nested f-strings. So like f-string containing another f-string, like let's say 1 + 1, and close this and close this. While in the previous Python versions, the nesting was limited by the number of different quotes that you could have. So there was this quote, then the triple quotes, these triple quotes, and then you are basically out of luck. So that's something that I also wanted to mention. Then another feature is that what we're gonna do is do this, and then we're gonna do this, or maybe do this, because now what Python allows you is to have multi-line f-strings, and you can also put comments here, right? In this way, which wasn't possible in Python before. And finally, let's get back. What we can also use are escape sequences. Escape sequences here. Yeah, I'm not gonna repeat that. Which wasn't possible in the previous Python versions, but it is possible. It is possible now. Okay, so finally we have Python 3.13. And the first feature that I would like to show you is improvements in the interactive interpreter. So let's clear this, and we're just gonna launch the interpreter. So what I've been using so far is Python 3.13 release candidate 1, because Python 3.13 wasn't released at the time of recording. And you can immediately see that there are some colors. The colors are also there when you raise an exception. So the name of the exception or the exception message, and also the some parts of the traceback are colored, which is kind of nice, and it makes the code, it makes the output more readable. Then another feature is that you can press F1, sorry, and this will bring you into the help subinterpreter, and you can type various functions like rematch or refindAll, and it will tell you the documentation, and you can switch back by exiting the help menu. Then another feature that is there, if you press F2, it will show you the history file, that .python history in your home folder, where you can see the statements that you put into the interpreter. And if you put F3, if you press F3, it will put you into the paste mode, which you can use to simplify copy and pasting, like multi-line code. And also the last but not least, my favorite feature is that you can now edit multi-line statements. So for example, if we create class A and we define a foo method, you can now press the up arrow and edit the class in this way. So if you remember from the previous Python versions, if you pressed the up arrow, you would basically circle through the multi-line statement through single statements, which made you unable to edit the whole multi-line statement, which is kind of nice. The other features is something that has been highly anticipated in the Python community for quite some time, and that is support for running without the global interpreter log, abbreviated GIL. And just to refresh your memory, what the global interpreter logs causes is that if you run multiple threads inside the process, those threads share the same global interpreter log, which prevents them from running in parallel. They still run concurrently, meaning that the Python context switches between those two, but you cannot utilize your multi-CPU or multi-core system in this way. So the Python developers are like aiming towards removing that global interpreter log, but even though removing the log is, let's say, simple, meaning that you have to just change some code, the issue is that you need to do this in a correct way, meaning that the interpreter behaves correctly without the global interpreter log. And also you don't want to take much performance hit, especially when it comes to single-threaded scripts and programs, because the benefit of the global interpreter log is that you just need to lock it at the beginning of the script, do this stuff, and then unlock it. So there's no need for more granular locking, which speeds up single-threaded code. All right, so as I said, the support is experimental, and for now, let's get back. You need, if you want to use it, you need to use a special build, which used the disable GIL parameter when building CPython from source. So I don't think that it's likely that popular distributions will provide like this build by default. Maybe they could provide two builds, like with the global interpreter log, like the default, and the new and the second release without the global interpreter log. And also the Python developers don't envision that this is gonna be enabled by default soon. Currently they are speaking about 2030. So maybe if you come to this video in the future, like in 2030, and we are still not there, well, yeah, we weren't there in 2024. And also the Python developers reserve the rights to remove the attempts to remove the global interpreter completely if they see that this is a dead end. But for now, we can at least play with it. So I have compiled my own CPython 3.13, both with the global interpreter log and without, and let me give you an example. So what I'm going to write is a very inefficient version of the Fibonacci function, just to have something that is computationally intensive. This way, an -1 plus fib and -2. Right. So please don't do this. This is really a terrible implementation. But anyway, I can now import the concurrent futures module and use its thread pool executor. So for example, let's put 12 here as pool. And now I can run the Fibonacci function, let's say, I don't know, 35 of the number 35, maybe 12 times. So each thread would receive a single Fibonacci or number which it's supposed to compute. So we can do this, and now we can time it. So Python 3.13, and if we run it with the global interpreter log, I'm sorry, just pi, it will take some time to execute, as you would imagine, because it is unable to utilize all the CPU cores. So it's running just only on a single core. So it's gonna take a while. Yeah, so 23 seconds. And now what we can do is to switch to the other build without the global interpreter log and see how long it will take Python to finish the code now. Yeah, and we can see that it took only 7 seconds to run. And yeah, this is a special, like the experimental free threading build that I told you. So yeah, this is what we've been waiting for, although it is not enabled by default. Let's see where the future brings us. And by the way, if you wanted to do this code like blazingly fast, with a terrible implementation of the Fibonacci function, you can use the memoization or caching in this way. I'm sorry, Python 3, and even without the it doesn't matter. Time pi, just pi. It likes run blazingly fast, right? Okay. And the final feature of Python 3.13 is another experimental feature, and it's support for a just-in-time compiler. So just to refresh your memory, what a just-in-time compiler, or JIT for short, does is that during runtime, it can compile the bytecode into machine code so that it can run directly on the CPU, thus making your code faster. And this can, given that the interpreter has context from the runtime, this can make the execution faster than what an ahead of time compiler would be able to do, given that it doesn't have that context during the runtime. So yeah, the support is also experimental, meaning that you have to enable it via a configuration flag when building CPython. And also right now, the performance is on par or similar with the performance of the non-JIT compiler, like with the default version of Python. So you cannot think of the just-in-time compilation as kind of silver bullet that solves all your like performance issues with Python. No, like Python is still like slow when compared to other languages. but there is some ongoing work to make it faster. So if you remember or if you use the PyPy interpreter, it also has a just-in-time compiler, but it's faster in some cases than regular Python. So this is something that maybe we're gonna see more in the future, depending how the work goes. All right, and now we have reached the end. I have listed some references that I've used, including links, so you can read the whole nitty-gritty details of what also is available in the other Python versions. And also you can read the Python enhancements proposals, or PEPs, which I highly recommend because they give you the motivation, the rationale, what was considered, and what was decided that, well, we shouldn't do this because of these particular reasons. So yeah. And by the way, I also wanted to cover Python 3.14, but at this time there are like almost non-existing features, or at least in the changelog. So I decided to stop here with Python 3.13. All right, so thanks everyone for watching, and see you next time.